What is it?
Immediately into the couple of something like that, it has to do something. It's a short list of information. Okay? From the real line to map into a triangle.
Yeah.
Something else. And he said, well, I never got the idea. It was very, 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 very difficult. Blah, blah, blah. Of course, I couldn't do it, so it's very, very difficult. Then I said, okay, what you are saying is that you cannot do it, therefore, it is very, very difficult and nobody else of us can do it. And he looked at me and said, yes, that's exactly what you said.
Yeah.
You have to give him.
He was, yeah, he has a very dry sense of humor. Are we going right now? Okay. All right. So let me. What's the password again? I think I remember. Okay. Okay. So let's. So we'll come back to this torus versus sphere thing later on. Let me. So now that we kind of know what homeomorphism means, let me give you a definition. So we were studying metric spaces a little bit, which form a very important and useful class of topological spaces. So a topological space is said to be metrizable. So now we can give a very simple conceptual definition using our notion of homeomorphism. Simply, if it's homeomorphic, to a metric space. Actually, we could have given this definition before the notion of homeomorphism, but this really is the right way to think about it. If you want a definition that doesn't use homeomorphism, it would go something like this. So equivalently, Actually, it's a nice exercise to convince yourself these are equivalent. It's not very long to convince yourself, not a very long problem to convince yourself of that. Equivalently, there exists a metric on the set of the topological space that generates in the way that we talked about before, that a metric can generate a topology using the open balls. So there exists a metric on the set that generates its topology. So it already has a topology. The question is, can you find a metric that actually generates that topology using the open balls? And that's the same as simply saying it's homeomorphic to a metric space. It's equivalent. Equivalently, there exists a metric on the set that generates its topology. So, I mean, this kind of a thing arises pretty naturally. So you can take R with topology, which is in fact the standard one. R with standard topology. You could say it this way: generated by the basis of open intervals. So you see, there's no mention of a metric here. Just so the collection of open intervals is a basis for a topology, which we call the standard topology. So is this topological space metrizable? Is it homeomorphic to a metric space? Or is there a metric which generates that topology? And yes, there is. It's the metric that we're used to. So this is, if you want to use the word homeomorphic, this is homeomorphic to, well, it's the same set as to R with topology So it is in fact a standard topology generated by the metric dxy is the absolute value of x minus y. What's the homeomorphism? I told you that the set is R, so it's kind of funny. It's very simple, but very, very useful to spend time thinking about this. So what's the map from R to R that is a homeomorphism between these two different, at least differently defined topological spaces? Well, actually, the two topological spaces have the exact same collection of open sets. So if even more than being homeomorphic to, you could say that the open sets are the same. So the homeomorphism is just the identity map. The identity map is a homeomorphism, which is another way of saying the topologies are actually the same. What is a topology? It's a collection of sets, of subsets of a set. So the collections of subsets of the set R, which are called open in these two examples, are 100% identical. The topologies are identical. So if you want to say that, actually we had talked about this before. Do you remember when we said that here's the topology generated by, actually we talked about this for R2. It works this topology, if you want to think of it this way, the topology generated by open intervals is actually equal to the topology generated by the metric. Same kind of thing happens in R2. We had spent some time discussing this. You can take R2 with topology generated by open rectangles. It actually, in the same way, equals the topology generated by the metric dxy. Well, in fact, back then we just called it this, dxy. We now know you can also think of it as this, although sometimes we put 2. It's not just absolute value, it's the norm of the vector x minus y. In fact, you can do this in Rn. You can take Rn with topology generated by, so you could think this is products of open intervals A1, B1, A2, B2, etc. until you have AN, BN. You can check this as a topology. You have to check this as a basis for the topology, and then you have a topology. So to use this word is metrizable. Metrizable. So this is homeomorphic to Rn. In fact, it's the same topology just like before. Homeomorphic to Rn with the topology generated by the metric, which is the same formula, the norm of x minus y. So the idea is you're given a topological space, it already has a topology, and you wonder, does that topology come from a metric? And that is equivalent to saying that it's homeomorphic to some metric space. Here's an important definition in mathematics in general, actually. A topological space is what's called a Hausdorff space, or has the Hausdorff property, something like that. If, and the definition is pretty simple, take any 2 points, so call it X. Take any 2 points, P and Q and X. There exists, let's call it XT. XT is the topology. For all points, P and Q and X, because P not equal to X, there exists open sets, so U and V, belonging to T, the topology, such that P is in U, Q is in V, but U intersect V is empty. So the picture, which will convince us that this is true, in R, that R2 has this property. So R2 is a Hausdorff space. If we just make this little picture, take PE here, here, here. So I could take U something like this and V something like this. But that's the idea in general. Now, so yeah, in fact, R2. So this picture is trying to convince you that R2 is Hausdorff. In fact, you can ask how far can you carry this? Well, in fact, it's not too difficult to see that all metric spaces are Hausdorff. Therefore, it's okay if you say that a metrizable space is Hausdorff. So metrizable implies Hausdorff. It's a nice problem if you want it. So remember, that includes Rn. We briefly talked about just the idea of any normed vector space. Any normed vector space is Hausdorff. In fact, discrete spaces have the metric, the discrete metric. So you know that discrete spaces are metrizable. So metrizable spaces include lots of examples. So in fact, Rn, we had mentioned that any subspace of Rn is metrizable. So you see there's lots of examples right there of metrizable and therefore Hausdorff spaces. So can we think of a topological space that's not Hausdorff? Here's one. It's called, so I guess this is known as the line with two origins. So we have to say what the set is. What is the space just as a set, first of all? Well, let's do it like this. So let's take the interval 0, infinity, closed interval, and we'll multiply by the set just containing 0. And then we take the union with so here's with 0, 1. Actually, it's the point 0, 1, not the interval 0, 1. I'll draw a picture in a second. The union with the set containing 0, 1, and then union with the set containing 0, minus 1. So in fact, what I'm giving you is a subset of R2. It looks like this. You have this line here, and then you just have 2 points here. And now the key, and this is where you have to think very carefully about the definitions, I'm telling you that X is a subset of R2, but I'm not going to give X the subspace topology because that would make it Hausdorff. Okay? So, however, not with the subspace topology from R2. So in fact, the topology is generated by the following basis. So in fact, open intervals like this where A is greater than or equal to 0. I'll draw a picture in a second. And, in fact, let me go back and let me call this point P and this point Q. Easier to refer to them as P and Q here. So, and sets where you take P union 0B times 0, and then the other type of open set in the basis is the same thing with Q. So Q union 0B times 0. So it looks like this. Here's my space. As a set, it's a subset of R2. So for example, this let's try and take advantage of the color. So here is an open subset. Notice that is like an open interval in R. In fact, this is an open set in the subspace topology as well. Now, the other type of open set, though, is something like this. I can take this point, and then I take an open interval like this that goes up to that point, but then it jumps to the upper point there. And then I have the same thing, but with the lower point. I guess that was called Q. So this is also in the basis. So that's the basis. So you take all possible unions. You have to check that it satisfies the rules of a basis, and then you take all the possible unions of those open sets. So in fact, what happens here, so I claim that this is not a Hausdorff space. It is a topological space, but it's not Hausdorff. What happens is that for all U and V open in the topology I was just describing, such that P is in U and Q is in V, so my P and Q are specific points. This is my P, this is my Q, this is my P, this is my Q. Not just any point. For all open sets U and V, such that P is in U and Q is in V, we actually find that the intersection is non-empty. So if you go back to the picture, you see in the lower two pictures are the basis elements, the basis open sets that contain P and Q, and as you see, they always contain points on the line portion of the space. So the intersection will always be non-empty. So in fact, in the next page, I'm calling this U and this V, and you see the intersection. The intersection is some set actually of the first type, right? So, well, let me draw it again. If you take something like this, and you intersect it with something like this, you get something like this. So X is non-Hausdorff. Is a non-Hausdorff Hausdorff, it still is a topological space, though. So our definition of topological space, which is abstract but simple, includes things like this in the definition. X is a non-Hausdorff topological space. So if we were asked to find a metric on X that generates this topology, is there a topology? So if a space is metrizable, it means that the topology somehow involves the idea of distance. Can we find a notion of distance on this space X that gives us this topology? No. It's a topology that exists, but it has nothing to do with distance. Okay? So thus we shouldn't even bother. If somebody asked you to find a metric on this space that generates the topology, we actually know that you would be looking forever. You would never find one because it's not non-Hausdorff. And I told you that a metric space or a metrizable space is always Hausdorff. Thus, we shouldn't even bother looking for a metric that generates this topology on X. You see, if you use the same set X, but with the subspace topology from R2, then of course you know it is metrizable. But using this topology, it's not. So Hausdorff okay, now here's a question. So does Hausdorff imply metrizable? Metrizable implies Hausdorff. Is it really if and only if? So have we just stumbled upon a very simple characterization of what it means to be metrizable? It simply has to be Hausdorff. Well, that would be very nice, but it's not true. And this is where things start to get really strange, and I don't even really know what to say about it. No, but it takes, let's say it takes some serious effort to find an example. So the space we just saw, which is not that strange, is, it's non-Hausdorff, and therefore not metrizable. If you wanted to find a space that still is Hausdorff, but yet not metrizable, it would be a space that's very difficult to describe. No, but it takes some serious effort to find a counterexample. So here's a question. Hausdorff. So we know that Hausdorff, well, I'm telling you, we don't really know, I'm just telling you, you have to take my word for it, that Hausdorff does not imply metrizable. So after understanding that, you would ask the following thing. So what else do you need to know about a space to make it metrizable? So Hausdorff plus what else implies metrizable? What other conditions can you add to make it metrizable? And this was a very famous problem in topology. So this is usually called the Uri-San, I don't know if I'm spelling this right, Uri-San metrization theorem. Very famous theorem. And it says what else is. I have to answer my phone right now. So we're going over. Hi, honey. I'll be wrapping this up in just a minute, okay? Okay, perfect. I'll be finishing in just a second. Okay. So this theorem tells you what the what else is. I'm busy. Okay. Okay, so the what else. it tells us what the what else is. The what else, so the what else is kind of strange, and this will be the strangest stuff that we talk about for a second. The what else is the following. The first thing, so the what else equals, first thing is that, so remember the idea of a basis for a topology. So you have to know something about that. So X has a topology generated by a basis of the form. So let me continue on the next page. So here I have UN such that n is a set, is an element of the natural numbers. So I'm saying here that you have a basis for the topology of X that's indexed by the natural numbers. That means that if you think of this collection, I mean, it is a collection of sets, that there's a bijection between that collection of sets and the set of natural numbers. This is called a countable basis. N is what's called countable. We're not going to talk more about what that means. You have to have a basis that you can index by the natural numbers. It's a countable basis. They call this, the X is called second countable. That's number one. Number two is kind of reminds us of the Hausdorff thing. It's that for all points, P and X, and closed subsets, let's say C and X, the rest of this now sounds exactly like the Hausdorff thing, that there exist U and V in T open sets such that P is in U, C actually is a subset of V, and U intersect V is empty. So let me draw the picture. Here's P, so here is C. So C is not a point necessarily, it's a closed set. And I have to be able to find two open sets that contain those things that don't intersect. So this is kind of like Hausdorff, but it involves a point and a closed set, not 2 points. Yeah. So note that, so this would be a stronger condition than Hausdorff if you knew what? If you knew that points as subsets of the space were closed. But that's where it gets weird, is that doesn't even have to be true. So this actually implies Hausdorff. If points are closed sets. That doesn't even have to be true. Okay. In this case, X is what's called normal. This is what's called a normal space. So what the Urisohn metrization theorem says, that the space that's Hausdorff and normal and second countable has to be metrizable. I can write that here. So Hausdorff plus normal plus second countable implies metrizable. That's the famous Urisohn metrization theorem. So that's the kind of the most abstract theorem that I'll mention. We'll come back down to earth next time. This is probably a good point to stop.